Welcome, everyone. And I hope already the tiny conversation was maybe a good start. Thank you all so much for joining this evening session of talks at PyData Amsterdam, or the PyData Amsterdam Festival for this year. And I'm very pleased to announce that our first speaker for tonight is Jim Dowling, co-founder and CEO of Logical Clocks. And he's here to tell us about Hopsworks.AI, which is also has an open source feature store for machine learning. Please, Jim, the floor is all yours.
Thanks. All right, so we're European, and this is open source. This is the open source session, and Hopsworks is an open source platform. And I'm going to talk in particular about the feature store aspect of it. So it's a modular platform for data science, and it contains a feature store. But we're going to talk mostly about that. And then this Hopsworks.AI part, that's the new SaaS version of our platform. And that's available currently on AWS. I think it's the only full stack AI SaaS platform from Europe currently. It's also a data platform. But we might have time for a little demo at the end. So let's kick off. Yeah, who are we? We're based in Stockholm primarily. We have one person in the Netherlands, and we have a couple of other offices. So I'm going to start by giving you a data engineering perspective. And I would say I fall more into the data engineering side, even though I've taught course in deep learning. Data engineers look at feature engineering and the work that data scientists do to train models. And I don't think they really understand the gap, right? So they have their data in databases, they have varchars, they have files, they have objects and object stores, and they have the SQL types. And the language they speak is the language of back-end data platforms. And the language data scientists speak is the language of NumPy numerical features, categorical features, and there is a gap between them. So what data engineers often don't understand is they think, well, I have my data in my operational database, and on the left you can see we have a database with a lot of hotel bookings in it. The bookings just have a start date, an end date, and then the room number. But the data scientists know that, well, I need to maybe compute or transform that raw data in features. So maybe I want to compute a feature like the load factor over a room. And that feature, load factor, it could be used in many different models. So it's not going to be used in just one to predict whether a room could be free or be occupied in a given period of time. It might be also used to predict revenue at the hotel over a period of time. So feature engineering, this process of getting your back-end data and making it available for models, is about transforming data. And sometimes we need to do it at scale, and sometimes there are edge cases that data engineers, again, don't understand. You might have some numerical features here. I'm just going to pull up a pen actually here, so I can actually highlight things. So you can see we have an array of features here, and it's a nice little, pull that up, close it. So it looks fine and clean, and maybe a data scientist will look at it and say, well, hang on, we have, oh, that's quite big. We have, like that, a little bit smaller. So any of that size small. Okay. So they look at that and say, well, this isn't ideal. We might have some numerical instability here. So I'm going to normalize those particular features. So you might decide to do that. Often what we'll see in the data engineering world is we might want to do it so that we'll scale. We have a large volume of data. And here we have a little code snippet doing that in PySpark. And there's framework support in PySpark for doing feature engineering at scale. So we have challenges of doing feature engineering, and then we have how to do it at scale. So what we have introduced is this thing called a feature store. And the feature store is this API between data engineering and data science. It's a place where the data engineers can cache or materialize these features. So the values of the features will be available there. And a data scientist can come along and say, well, I like those features. Maybe we have the load example from our hotel room, or maybe in this case, we have the Titanic example. So we have the Titanic passenger list here, and we want to, and that tells us whether passengers survived or not, and we have features like the sex of the passengers and whether they're in first class or second class. And we can imagine that somebody has done some research and found out the bank account balances of the people on the Titanic, and that data comes in from a different source, a different platform, but we put it in the same feature store. So the idea behind the feature store is that data scientists can come along and just take features and reuse them in different models. So what they'll do is they'll take a bunch of features And in this case, the data scientist might say, I'll add that bank account balance to the Titanic passenger list data set. And now I'll have a new data set with this bank account balance as a new feature, which will hopefully help me predict a little bit better if a passenger survived or not, because I have a hypothesis that if they had a lot of money, they bribed to get on the Titanic. Now, this looks a little bit intimidating if you're a data scientist. We have join keys and we have arrows pointing everywhere. And here, there, I'll show a little code snippet in a little bit to show you it's a lot simpler than that. But what data scientists want to do is they want the flexibility to say, okay, I'm joining these features together, but I want the output, the data. I'd like either maybe I just want the NumPy array, maybe as a file, or maybe I just want a pandas data frame, which I can get directly in my application and work directly from there. But often when you have large volumes of data, you might want to train on deep learning with TF record, or you might want to use CSV for whatever reason, or even a scalable file format like Petastorm. Then you also need to decide where am I going to store this data. So you might decide to store it in S3 if you're working in Amazon. We have our own file system. There's GCS and there's Hadoop. There's plenty of different file systems to store your data in. So yeah, let me have a look. There was a little bit of flashing. No questions yet. You can just pop in a question in the Q&A and I'll have a look at them if there's anything appears there. Okay, so I haven't said much about what the features are that we work within. What I'll try and do here is give a quick taxonomy of the types of features you have. So you have some features that arrive with low latency, so they're being updated all the time. Or maybe it's data that arrives that we don't have enough time for that data to push it into the store and pull it out in our model itself. So if, for example, we have a data arriving on a web page and a user has to enter that data, we need to transform that data into features and then make a prediction, and we've only 2 seconds to do that. So in that case, we typically won't materialize that feature to the feature store. We'll just push it straight through. But for other cases where we have data, for example, that arrives every few seconds or every 30 seconds or every hour or every day, well, in this case, we can have a pipeline. So we can have different pipelines, a streaming application pipeline. We can have a Pandas application pipeline or a Spark application pipeline. And they'll push that data, and depending on the type of data, so if it's click data, it might come very frequently. CDC data from a database, an operational database, it might come quite frequently. But then things like weblogs don't get updated that often. So these types of features will end up in the feature store. And then what we'll have is we'll have our online application here, which will be able to say, hey, I only have 10 features available through real-time transformations, but I need another 100 features to train to make predictions. So please give me those 100 features, and give them to me at low latency. We saw the example already of data scientists who would like to train models. They'd like to generate training data. Batch applications like Spark applications or PySpark applications, they can also just pull data directly from the feature store. So we have 2 different requirements here. One is that we have this low latency requirement for serving features, but we also have the requirement to scale to large volumes of data. So we have one customer in Sweden, the largest bank, Swedbank. They have 40 terabytes of transaction data. They talked about at the last Spark Summit. So no database that's out there right now that we're aware of has this scalability to petabytes and very low predictable latencies for feature serving. So what we end up doing is we end up dividing up our feature store into a dual database architecture, an online feature store for caching the online features that will be accessed by online applications, and then this scalable SQL layer we call the offline feature store that will be able to store large volumes of data. So what we introduced in our platform because we already talked about this notion of groups of features that are computed together, and we talked about training data sets and individual features. Well, this feature group abstraction that we introduce, what it's there to do is to simplify storing your data to both the online and offline feature stores. So what we introduce is, in fact, a data frame API. So the feature engineering pipelines over here will push data frames. So they can be Pandas data frames, they can be PySpark data frames, or just Scala Spark data frames, but they get pushed into the feature store. So now the developers of feature engineering pipelines don't need to worry about synchronizing data between an offline and an online store. They just say, I'm going to update this feature group, or I'm going to create a new feature group, and here's the data frame containing the data for that feature group. We have some cases where we have feature pipelines that don't go directly to the feature store, but what they can do, for example, at one customer, we're using Flink to do real-time feature engineering. But what Flink can do is it can push the features that it computes in the background to the offline feature store. So we can still gain the benefits of it, even if the online features are computed in real time and they don't go through the feature store. Okay, so yeah, so we have this general purpose data frame API that we use to ingest into the feature store. At this point, I should mention that some of you may have read about feature stores from Uber or from Airbnb, and they have domain-specific languages that they provide for doing feature engineering. And when we looked at this, we did release the first fully open source feature store at the end of 2018, but we wanted a general purpose framework. So we didn't want to specifically do feature engineering for given domains, which is what they're kind of doing. And that's where we ended up on the data frame API. Okay, so I promised you a little bit of code. So here's a snippet. And here we have creating a feature group. Feature group is here, it has a name. We actually have a lot more parameters, as you can guess, in here. So one of them is online equals true. So if you write online equals true, it's also going to create this feature group in both the online and offline. By default, offline. Okay. And what we can see here is that we have this data frame, which is being read up. And I'm not specifying where it's coming from. You can have derived features which read up data from the feature store, or you can have base features which read up raw data sources, the backends, the data lakes, the data warehouses, the operational databases. So our data frame will read the data from someplace. You'll do your feature engineering on it, and then all we do is we call this feature store.create feature group with our data frame as a parameter and a name. There are other parameters in here about computing statistics over your features as they arrive. Statistics. So you want to know descriptive statistics, you want to know distributions of individual feature values, and they get computed automatically. You can turn off computation of them. We've been using Spark to do that computation, but we're now moving over to a library called DQ for that. Okay, so this is where we kind of are. We have this feature store. We've looked at the ingestion of data into the feature store. And now we'll have a quick look at both online applications, how they use it, and then also how we generate training data sets for users. Okay. So creating training data sets for users, we are actually using Spark as the compute engine. So what we need to do is we need to take all of these features, and we have this little code snippet here. This is assuming a flat namespace of features. So in this flat namespace, assuming there's no clashes between feature names across feature groups, and we do support scoping in our latest API, what the feature store will do is it has a query planner that will look for the feature groups associated with these features. It will look for a common, it'll look for the largest overlapping set of primary key columns between them, and then it will join them together. And we're actually using Spark as the engine to do that. Now you can call this from an external Jupyter notebook, for example, running on Kubeflow or just a normal Jupyter notebook or on SageMaker. But what it will do in that case is it will actually run the Spark job on our cluster. If you have your own Spark cluster, you can run it on your own Spark cluster like Databricks or Hadoop. So what happens when you call this feature store.get features is it's basically reading up each of the feature groups as data frames and then joining them together, like I said, using the query planner. You can specify the join keys that you want to use, and they may be multi-part join keys. You can even override the type of join you'd like to do, which is by default an inner join. But then you have to basically decide where to output that. You're going to get back at basically a large data frame, and that data frame, you can say, I'd like to have it in pandas, or you can say, just please materialize it to a file system or an object store as this file format. So what a data scientist will do, and this hopefully should save data scientists a bit of work, is that, well, firstly, they'll browse the feature stores for features. They'll look at distributions of feature values, get an understanding for them, and then decide to create training data. So this is a data frame. And we have another parameter here which says pandas equals true, which means you want a pandas data frame back. If you don't, by default, it'll be a PySpark data frame, and it'll assume that this code is running in a Spark environment. And the other call, if you're just running in a Python environment, is it'll make a REST call in our platform. And then when you call create train data set, it will run a job on our platform to do the join for you and to actually then save the output data in the file system that you want to use. So that's what this second call is doing, fs create training data set. It's actually going to materialize it. So we specify our file format. Everything here is versioned. So train data sets are versioned, feature groups are versioned, and features individually are versioned. Now, this is a little a preview for a new API we're releasing at the end of this month. And we've made it a little bit more complex because I said that, well, this assumes a flat namespace of features. Well, what we've actually done is we've introduced feature groups as a kind of a first-class entity now to make it easier for users to scope their features. So if, for example, you have two features with the same name, so maybe the name of that feature is ID, but if it belongs to a feature group, so maybe the features group name is Titanic, so we have a scope now, Titanic/ID, and maybe we have then the bank account has an ID feature as well. So these are two different features, two different feature groups, sorry, but they have the same feature name. So what we do in this case is, and this is a more Pythonic API, is that we get back feature groups. So we have two feature groups here, and what we can do is we can basically say, select all of the features from the Titanic feature group and join them with all of the features from the bank feature group. And again, it will use the query planner to find the largest overlapping subset of primary key columns between the two feature groups. So this data frame that you get back, you can again, same as before, you can materialize it to, in this case, materializing it is done by calling td.save. So the training data set is actually in the new API, it's just a metadata object, and you need to call save on it to actually then, so it's lazily, it's not going to actually save that data frame until you call td.save. So in this case, we have an example showing a connector. So how do we use an S3 bucket? Well, we define a connector for it, or we read up a connector for it, and then we specify that as the output. That's where we're going to put it. And also in the new API, you can automatically specify the splits in your training and test and validation data sets. So that will be a random split data. Okay. Do I see no Q&As yet? So I'll keep going. Okay, so here's something that is a little bit more esoteric, but we do support something called time travel on feature groups. So we have this abstraction of feature groups, and feature groups can get updated. They get updated every hour if you have an hourly update, or every 30 seconds or minute. For feature groups that get updated more than every minute, so maybe every 10 minutes, we can use this hoodie storage format. So it's effectively, it's a layer on top of Parquet, which is a file format. And it supports atomic updates to these feature groups. It also supports incremental updates, and it also supports the ability to do what we call time travel, to say, give me the data as it looked at this point in time. So at this commit, which you can also supply with a timestamp, or you can also say, give me the range of data that arrived between these two time intervals. So in our case, the API looks something like this. I can say for a feature group, I can say, I would like the Titanic feature group as it looked like at this moment in time. And I can also say, give me the data that arrived into the bank feature group, this start time and this end time. And then we can work with these feature groups as before. We can join features across them and then materialize them. So this, a good example of this would be, for example, if you want to take training data to be between the years 2012 and 2017, and then your test data 2018, well, you can just get the data that arrives in that range for the training and the other one for the test. So we move on. The online feature store is how online applications access this feature store. In our case, we provide a JDBC API. So the online applications can start up and say, hey, I would like to get back what we call a prepared statement, which says, this is all the features that make up the feature vector that I'm going to send to the model for predictions, but I'm missing a lot of the feature values. So that query is going to get sent over JDBC to the online application, to our online database, our online feature store. and it will return back the entire feature vector. So the online application may be missing a bunch of features, it gets them back, and then when it has the feature vector, it can send it to the model for prediction. Now this could be done as well inside the model if you want, or it can be done in the application, and it's pretty flexible framework going into it in one or the other. So in the cloud, all of this is HA across availability zones, both for model serving and for feature serving. So how this looks in practice is in a little bit more detail, is that our online application here will have some primary keys. So maybe it's user ID, shopping cart ID, it might be the Titanic passenger name, something like that. And those keys are the primary keys that we're going to use to look up the feature groups effectively. So what you do is when you start up is you say, well, here's the name of the model I trained, or here's the name of the training data set that I used to train this model with. Give me back a prepared statement. And then that prepared statement will be filled in with the key values that you supply. And from there, you'll get back your feature vector, and you can send it then for prediction to the model. I'm going to take a question a little bit. Is it possible to apply more filters than time while reading the data? Yes. So when we create feature groups, you can just apply lambda expressions as feature. You can call filter on it, and then have a lambda expression to filter out the data you're not interested in. Okay, so the feature store is part of Hopsworks. Hopsworks is slightly bigger than just a feature store. You can use it to train models. You can even plug in Kubernetes to serve models and monitor models. And then we support Spark and Flink for doing batch processing. And there's even Kafka, a file system, and Airflow in there. So it's quite a complete platform. It runs on premise and in the cloud. But I'll just show you how this fits. The feature store fits into an end-to-end pipeline. Taking your raw data, this is our raw data here. So our raw data is in our data lake and our data warehouse and our Kafka topics. And what happens is we looked at feature engineering to get that data into the feature store. And at the next point, you need a data science platform. And what you typically will do is you'll select a bunch of features, and then these features, you'll materialize them, but sometimes you'll just have a pandas data frame and you'll train directly on that. And if you've materialized them, then you'll have another notebook, for example, to train the model. And then you'll need a next step to validate your model, so to do model analysis, scoring of your models. And if they're good enough, you'll publish them to a model repository or model registry. So our platform includes all of these parts. We even have support for experiments like MLflow. If you have a model registry, batch applications can use them directly, but you also often want to deploy those models to serving infrastructure. So the key point here is that the feature store will supply features with low latency, either directly to the model or to the application. You need to build the feature vectors in order to be able to make your predictions. And things that are important are things like, if you're using NumPy, well, how are the features ordered in that NumPy array? So we let the feature store handle that. The platform is a little bit more than this. There's things like multi-worker training, asynchronous hyperparameter tuning, project-based multi-tenancy. You can read up on it on our website. We have a provenance. You can try it out. So it's free right now to try out Hopsworks.AI. It'll be free for the summer. And there is a community version you can just install. It's completely fully featured. And the licensing model is AGPL v3 for open source. And we do provide an enterprise version where we provide a few connectors for things like Kerberos, so Active Directory, and GitHub support and Kubernetes integration. I'm not going to go through this demo, so what I'll just show you is the platform and just show you a couple of seconds how to get started. It'll take 2 minutes. So this is Hopsworks.AI. You can just register here. And when you register, you can either get a demo instance that you can just play with. And this is, you can connect your AWS account. And when you connect your AWS account, you can then create a cluster. And you can create it wherever you want and click your way through to your cluster. But I'm going to skip creating a cluster. I'm just going to show you the platform directly. So this is an instance running here. I'm not sure what region it's running in, but it's running somewhere in the cloud, I guess. And I've already logged in, so I just logged in again. This is the project I was going to show you. It's called Churn. You can create many projects here. They're like GitHub repos. If I click Churn, it's in my GitHub. If you go to Jim Dowling /churn, you'll find the code for this. But this particular example is it's a telecom churn data set, and I created a feature group from it. And you can see if we have a quick look at the feature group, you can see there's a lot of features in here, and these are the distributions of the different feature values down here. But we also have things like correlation matrices we compute, and this is quite a big one. It'll take a couple of seconds to show that. So just clustering analysis. So these are pre-computed when we ingested into the feature store. And there's distributions of features. You can do data validation, add storage connectors, an overview with 47 features in that feature group. You can do individual features, and then you can even create trained data sets from the UI if you want to. If you want to try it out, you can use Jupyter Notebooks in here. And what's very interesting is that we can actually make Jupyter Notebooks into jobs. And you can have a bunch of jobs, like we talked about. Selecting features could be one notebook. Another job could be training a model. Another one be validating a model. And then you can even turn that into an Airflow workflow. We have a UI support for just adding jobs in your notebook jobs into that workflow. So that's a brief overview of the platform. There are other support for things like experiments. I don't have any here to show. Model surveying and models. I don't have any in here, I don't believe. But you can check it out in your own time, and we have plenty of material on our website. So with that, I'll say thank you to you for listening. You can find out more on our GitHub repo, logicalclock/Hopsworks. Feel free to fork it, contribute. We're on Twitter, and a lot of people have worked on this platform. With that, I say thank you, and I notice there's a question, so I'll take the first question. I think we have a couple of minutes left for questions. So how is GDPR sensitive data managed, as in that's separated in some way from non-GDPR data? That's a really good question. So firstly, the data inside these projects is completely isolated. So if I have many projects, I can't read data from the other projects while I'm inside this project. So if I run a notebook or a job in here, I get a new user identity for every project. So we're using TLS certificates internally to identify users. And your user identity when you run a job is the project name, in this case churn, and my username squashed together. So if I have two projects, I have two users. So if I want to explicitly share data between them, I have to actually go to my feature store and say, well, I'll share this feature store with another project. You can do that. The other thing that we can do is, which is very nice, is in the feature store, we can tag data. We can tag these feature groups. So this feature group here is telecom. Well, I actually added a tag to it called privacy level PII. And we can search globally across any, you might have a development, a production feature store, a staging one, but we can search for PII. And I can even do partial searching. So I go PI. It's syncing that to, and then it finds it, right? So I can find all my features that are PII this way, for example. I think we have another question, a couple coming up. All right, great. So if my data is on Google Cloud, then can I still connect to this platform? Well, you can install the platform on Google Cloud, and it can read from, so when you install it on Google Cloud, it'll read from GCS for you. So I think if you go to our read the docs, so Hopsworks.read the docs, there's installation instructions for installing the community version on getting started. I think it's 3 lines. It's like, you can just create a VM and just do this. There is actually early support for spinning up the VMs. If you clone a repo called Caramel Chef, we have a script that will spin up a VM and then install it for you. But if you just spin up a VM yourself on Google Cloud or GCP, you can run this and it will install the platform there. One more question. Right. All right. Well, that's that one. I think I'll answer that. Okay. I think any more questions? Is it possible to store features in Azure, for example, blob storage? So we support Spark in the platform. I didn't go into too much detail, so you can run Spark jobs. When you install, we're running Spark on top of Yarn currently. And in the Yarn environment or the Hadoop environment, there are loads of connectors for everything from, you can read in your data from, S3 or GCS or Azure Data Lake or Azure Blob Storage. That's no problem. We haven't moved to Kubernetes yet for Spark because basically Kubernetes doesn't work well enough. Shuffle in Kubernetes and Spark is just not good enough. We may eventually move to fully Kubernetes when that problem has been resolved. Again, you can. So the thing that's a little bit different about installing in Azure is that you have to add support for private DNS zones. We have some scripts that will do that for you. But the Azure VMs don't come with private DNS, which is a bit weird. So you don't get fully qualified domain names. Because we're using certificates, we need fully qualified domain names, so we need that from Azure. And could you integrate with MLflow, for example, if your system is already using MLflow for serving models? So MLflow does not serve models. MLflow is for managing experiments. I wish I had a UI, a demo instance to show you. You'll have to tune in to another episode. But what we do is we actually support something very similar to MLflow. We had a couple of talks, I think, about it recently. So what the issue with MLflow that we had was that you have to rewrite your code. You're polluting your code with all these logging statements, and you have to put your code inside a scope to run it. So what we do is, because everything is going through our file system, what we do is, for example, when you save a model to our file system, well, we know that happens. We have a CDC API to our file system, and then we just store that event, that this particular model was stored in this particular folder, so we know the version of it, and we know the application, because we have the application ID from Yarn, and we know the train data set as well that was used to train that model. So we're collecting a lot of that, and we call that implicit provenance. You can read up. I think we had a paper at a SysML workshop recently, and we had a talk, I think, late last year on it. MLflow is still good. I mean, awesome. It's nice.
Right. Thank you so much, Jim. Yeah, thank you so much for an amazing talk. That was very interesting, and I'm very much looking forward to having a bit of an easier life in my work as a data scientist going forward. Thank you so much for your work and for your talk, and great to have you here over here.